Hi students, good morning. Welcome to this video session. My name is Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall discuss the second method of solving a system of linear congruences. In the first video on solving a system of linear congruences, we used the Chinese remainder theorem. In this video, we shall do the same problems we did in that first video. We shall do it in this video. However, we shall be using the back substitution method. To be honest, I prefer this method to the first method. I prefer this method to the Chinese remainder theorem. So we are going to do those two same questions we did. We shall do that again in this video. We shall check our work, and then you can, like I said, the transcript of this video would be found on this website, modular-arithmetic.appspot.com. www.modular-arithmetic.appspot.com. So, and the calculators to check your answers are also on this website. So, like we discussed in the video on the Chinese remainder theorem, say you have a number, and when you divide that number by 5, the remainder is 4. When you divide the same number by 7, the remainder is 6. Okay? So the example one, the first one we did in that video. So we have a number, a positive integer. When you divide the number by 5, the remainder is 4. So this means that x is congruent to 4 in mod 5. And when you divide that same number by 7, the remainder is 6. X is congruent to 6 in mod 7. What is the number? What is the positive integer? So, like we said in that like we said in that video, in the one on the Chinese remainder theorem, this was the first example we did in that video. In this case, in the back substitution method, it has to also be the modulo has to be relatively prime. Okay. The modulo also has to be relatively prime. So when we have x congruent to a1 mod m1, x congruent to a2 mod m2, okay, x congruent to a3 mod m3, up to, no matter it is a system of linear congruences because it's more than one congruence. Okay, more than one linear congruence. So we call it a system because it's more than one. It could be as many as you want. So up to x is congruent to a subscript n mod m subscript n. So the condition is that the condition which applies to the first video is that the conditions is that number one, that m1, m2, in this case we shall not, there are some, just a little bit which this is a different method, but some basic conditions will still apply. M1, M2, M3, up to Mn should be relatively prime. Okay, should be greater than 1, okay, and relatively prime to one another, relatively prime to one another. Okay, they have to be relatively prime to one another. When you check your work with the calculator in this website, if the modulo are not relatively prime, it will give you a warning, or it will give you a message, not a warning. No, it will give you a message that hey, it has to be relatively prime. So the modulo has to be relatively prime. They are positive integers greater than 1, positive integers greater than 1 are relatively prime to one another. Positive integers greater than 1 are relatively prime to one another. Number 2, the A1, the numbers A1, A2, A3, up to A subscript n are positive integers. Positive integers. Okay, so these are the conditions. All right, so let's review some concepts. We see that 5, let's say 5 mod 3 is what? 5 mod 3 gives you 2. Right? So we say that 5 is congruent to 2 in mod 3. Remember, that was the way we said it. Okay, if you, please, it is important that if you go to this website, you click on videos, and you start, is a video playlist. You start from the first video, okay, to have a good knowledge of this. Okay, so you remember this concept in linear congruence. 5 mod 3 is 2, so we say that 5 is congruent to 2 in mod 3. Now, what this also means, is that 3 can divide 5 minus 2. Okay, 3 can divide 5 minus 2. That is what it means. 5 minus 2 is divisible by 3. That is what it means. It also means that 3 can divide any integer k 5 minus 2. Okay? Where k is a positive integer greater than 1. I mean, where k is a positive integer, I would say greater than 0. Okay? So 3 will divide 2 times 3, 3 will divide 3 times 3, 3 will divide 4 times 3, 3 will divide 5 times 3. So that is what it means. This is what it means. So this also means that 5 minus 2 will give us 3. Okay? That 5 minus 2 will give us 3. That is what it also means. That 5 minus 2 will give us 3. And because I want you to understand this concept, because we are going to use that concept here. We are going to use that concept here. So this, if you bring this concept here, okay? If you bring this concept here, we start from here. Okay? We start from here. Now, you see here, at least you agree with me on everything we've done here. Okay? If it's not 5, like let's say now, here at least we have 5, but if we have a variable, okay, like we have it here, as you can see here, we have, instead of 5, we have the variable x here. Okay, let's bring this idea here. We'll start from here. X is congruent to 4 mod 5. So this actually means I want to convert this congruency to an equation. What this means is that x minus 4 is equal to 5. That is what it means. That is what it means. Okay? Just like we have 5 minus 2 is equal to 3. 5 minus 2 from here. From here we have that 5 minus 2 is equal to 3. That is from here. As you can see. That is what it means. Now, and this means that 3 will divide 5 minus 2, okay? But it must not be, like, what if it wasn't 5? What if it was not 5? Okay? It could be, the next one could be 2 times 3, which is 3 will divide 2 times 3, so 3 will divide 6. 3 will divide 3 times 3, 3 will divide 9, 3 will divide 4. K could be any integer. So, but in this case, this is 5 minus 2. What if it was not 5? So what am I trying to say? What I'm trying to say is that this can apply to several integers. If we don't have 5 here, let's say we have p here, okay? We could say p minus 2 is 3 times 1, p minus 2 is 3 times 2, p minus 2 is 3 times 3, p minus 2 is 3 times 4. So here, x minus 4 is 5, at least you see that. This also implies that x minus 4 is 5p, where p is an integer. That's the thing, okay? X minus 4 is 5p, where p is a positive integer. Where p is a positive integer greater than 1. Okay, p is a positive integer greater than 1. Where p is a positive integer greater than 1. Greater than 1. I mean, we can say greater than 0, like I put here, that's fine. Okay? If it's greater than 0, then it's 5. So let's put greater than 0, that's okay. Greater than 0. P is when p is 1, then it's 5. But p could be any other thing. P could be any other thing. Okay? So this means that x is equal to 5p plus 4. That is what it means. That x is equal to 5p plus 4. I'm going to put this as equation. X is 5p plus 4. And let me call this equation 1. Equation 1. Okay? And you could try, you know, we can try with several factors. I mean, we're going to check this anyway after we solve this. So what I'm trying to explain by writing this first, because I'm trying to find out the best way to explain it so that you will understand it. You understand the basics, at least. You understand the basic. When you have 5 congruent to 2 in mod 3, you can easily turn it to equation 5 minus 2 is 3. Now, you said you know this because it's 5. It must not always be 5. It must not always be 5. Okay? So it could be 8. 8 is also congruent to 2 in mod 3. It could be 11. 11 is also congruent to 2 in mod 3. So it must not always be 5. We had this because we had that is 5. Now, why did I say 8? Because I just did 5 plus 3, 8. 8 is congruent to 2 in mod 3. I did 8 plus 3 again. So this is like 3 times 1 is 3. 3 times 2 is 6. 3 times 3 9. So first of all we had 5. Then you do 5 plus 3 8. Then you do 8 plus 3 11. Now we had 5. Then we had 5 plus 3 is 8. We had 8 plus 3 11. But we could also say 5 plus 3 times 1, 5 plus 3 times 2, 5 plus 3 times 3. Do you see what I'm saying now? 5 plus 3 times 4. So that is the same approach here. If you have 8 is congruent to 2 in mod 3. You had 3 times 2, 6 plus 5, 11. 11 is congruent to 2 in mod 3. 3 times 3, 9 plus 5, 14. 14 is congruent to 2 in mod 3. So it must not always be 5. It must not always be 5. In this case now, this instead of the 5 we have our x. Instead of the 5 we have our x. So what we do is, we know now that we just did x minus 4 is 5. That's the basic, just like we did here. 5 minus 2 is 3. Now this x minus 4 could be 5 times other ones. Okay, 5 times p. P could be anything. Okay, if we have p to be 1, then that would be 5 plus 4, 9. 9 is congruent to 4 in mod 5. If we have p to be 2, 5 times 2 is 10. 10 plus 4 is 14. 14 is congruent to 4 in mod 5. Okay, when we have p to be 3, 5 times 3, 15. 15 plus 4, 19. 19 is congruent to 4 in mod 5. Okay, when we have p to be 4, 5 times 4, 20. 20 plus 4, 24. 24 is congruent to 4 in mod 5. So do you see it? So I don't want you to be confused. Just if you can just learn this here, the way I just did this here, if you can learn it, whenever you have x congruent to 4 in mod 5, just know that this x minus 4 is 5, and it could be 5 times p, because this is what we need here. This is the main thing that gives us this. So x will be 5p plus 4. This is our equation 1. Okay. So the next thing we will do is, that we will substitute 5p plus 4 for x in this second congruence. Okay, let's call this congruence 1, congruence 1, and let's call this cong 2, congruence 1 and congruence 2. So we take the congruence 1, make it as an equation, then we substitute this equation in congruence 2. Okay, so this is what I mean. Substitute 5p plus 4 for x in congruence 2. Okay, so where I see x, I now put 5p plus 4 is congruent to 6 in mod 7. 5p plus 4 is congruent to 6 in mod 7. Now, we subtract 4 from both sides. Okay, subtract 4 from both sides. So 5p is congruent to 6 minus 4 in mod 7. So 5p is congruent to 2 in mod 7. Okay, we can't just divide both sides by 5, no way, no. So we will solve it now as linear congruence. Remember what we did? We find the inverse. So we now have to find the inverse of 5 mod 7. Inverse of 5 mod 7. That is what we need to do. So we can multiply both sides by the inverse. Okay, so we have here, we look at GCD of 7 and 5, 5 and 7 will give us the GCD of 7 and 5. So please, that is why I said you need to view this from the beginning. Okay, so let's find the inverse here. So 7 is 5 times 2, 5 times 1 plus 2. Okay, 5 times 1 plus 2. And then 5 is equal to 2 times 2 plus 1. 2 is equal to 1 times 2 plus 0. So our GCD is 1. But to find the inverse, we start with this one. Please, if you do not understand what I just did now, please go to videos and start from the beginning. Okay? Importante. Muy importante. Very important. Okay? So, but we are not worried about the GCD. We want to find the inverse, so we can solve this congruence. So we start from here. 1 is 5 minus 2 times 2, which is 5 minus, this 2 is 7 minus 5 times 1, that's this 2 here, then times 2, times this 2. So this will be 5 minus 7 times 2 minus plus, because this is minus, then minus times minus plus, plus 5 times 1 times 2. So this is 5 times 1, this is 5, which is 5 times 1. Then plus 5, 1 times 2 is 2. Minus 7 times 2. Minus 7 times 2. So this is 5, 1 plus 2, 5. Parenthesis 1 plus 2 minus 7 times 2, which is 5 times 3 plus 7 times negative 2. Okay, we are interested in inverse of 5 mod 7. That is what we are interested in, inverse of 5 mod 7. And this gives us 3. So inverse of 5 mod 7, inverse of 5 mod 7 gives us 3. Okay, this gives us 3. So what we now have to do is we multiply both sides by 3. We have to multiply both sides by 3. So we have 5 times 3 times p is congruent to 2 times 3, then a mod 7. Okay, 5 times 3 is 15. 15 mod 7 will give us 1. 15 mod 7 is 1. Okay? So because this is, let me show the steps here. So this is 15 times p is congruent to 6 in mod 7. Okay, so 15 mod 7 gives us 1. Because this is 15 mod 7, this actually means, what this means is 15 mod 7 times p mod 7 is congruent to 6 mod 7. That is actually what it means. That is what this means. Okay? This is what this means. So 15 mod 7 is 1. Okay, so P mod 7 is P because we don't know what is P. So we want to find it. So we just multiply that. So we now have 1 P mod 7. We don't know what it is, so we just say it's P. Okay, so we have 1 times and 6 mod 7. 6 mod 7 is 6. Okay, so we now have from here, we now have that 1 times P is congruent to 6. 1 times P equal to, because this is P mod 7 is congruent to 6. So we can just say here, P mod 7 is P mod 7, because we don't know what is P. We don't know what is P. So P mod 7 is congruent to 6. Okay? So P is 6. P is 6. Because 6 mod 7 is 6. 6 mod 7 is 6. So our P is 6. Now we found our P. We found our P. So let me circle it with yellow chalk because we will use it. We're going to use it. We will now substitute this here to find our x. Okay? So we found our P. We now say substitute. Can we write it here? Substitute P equal to 6 into equation 1. Substitute P equal to 6 into equation 1. So this means that x is 5 times 6 plus 4. So x is 30 plus 4 and x is 34. So this becomes our answer here. X is 34. And if you do 34 divided by 5, it gives you 6. Remainder 4. Okay, it's because 6 times 5 is 30. So 6 remainder 4. And if you do 34 divided by 7, 7 times 5 is 35. 7 times 4 is 28. It gives you 4. Remember, 34 minus 28 is 6. And that's it. And this was the answer we got with the Chinese remainder theorem. Okay? So what we just did is convert get the first congruence, convert it to an equation, substitute for that equation in the second congruence, find the variable P, and then substitute back to get your x. That is all we did. Okay? Now let's do question 2. 3 congruences. A system of 3 linear congruences. So with 3 linear congruences, you have to be a little bit careful. We are going to use the same method, but we'll use the same process. Okay, let's do that. But it's the same process that we'll use to get our x. So this is actually back substitution because after getting our P, we go back to substitute it. It's still substitution method. Okay. Let's do the example 2. System of 3 linear congruences. Example 2. So we have the one we did with the Chinese remainder theorem video. We did x is congruent to 2 in mod 7. X is congruent to 3 in mod 9. X is congruent to 3 in mod 9. X is congruent to 5 in mod 10. 5 in mod 10. Okay, let me call this congruence 1, congruence 2, congruence 3. Okay? I start with 1. I start with 1 from congruence 1. X is congruent to 2 in mod 7. Let us convert it to an equation. And so x minus 2 is equal to 7. Okay, that is what it means. You saw it. Now also, x minus 2 is equal to 7p, where p is a positive integer greater than 0. Okay, if you can, as you can see here, when p is 1, it is 7 times 1, 7, plus 2, 9, x will be 9. 9 is congruent to 2 in mod 7. When p is 2, 7 times 2 is 14, plus 2, 16. 16 is congruent to 2 in mod 7, okay? So it's good you do it like this. X is now equal to 7p plus 2. So I'm going to call this now equation. This is now an equation 1. Equation 1. Okay? We are going to substitute equation 1 into congruence 2. Congruence 2. So substitute equation 1 into congruence 2. That is another way you can say it, okay? Or you can can also say it this way: substitute 7p plus 2 for x. I mean, this is the actual way to say it, but you can say it like this, no problem. Substitute 7p plus 2 for x in congruence 2, which means anywhere you see x in congruence 2, just put 7p plus 2. Okay, put 7p plus 2. So we have our congruence 2. X is congruent to 3 in mod 9. So we just put 7p plus 2 congruent to is congruent to 3 in mod 9. Okay? Subtract 2 from both sides. So 7p is congruent to 3 minus 2 in mod 9. So 7p is congruent to 1 in mod 9. Now we have to find the inverse of 7 mod 9. Okay, inverse of 7 mod 9, because we need it. So we need to find inverse of 7 mod 9. Okay, so let's do it. So we have, let's get our GCD of 7 and 9. I mean, I know it's 1, but we need it to get the inverse. So GCD of 7 and 9 is the same thing as GCD of 9 and 7. So 9 is 7 times 1 plus 2, right? 7 is 2 times 3 plus 1. 2 is 1 times 2 plus 0. So the GCD is 1. Okay, but we will need to work from here to get our inverse. So from here, 1 is 7 minus 2 times 3. And this will be 7 minus the 2 is, we'll put the parentheses, 9 minus 7 times 1. Now times this 3. Times the 3 here. Okay? So this is 7 minus 7 times 1. You can put 7 times 1. Okay? Minus 9 times 3. Then minus times minus plus 7 times 1 times 3. So this is 7 times 1 plus 7 times 1 times 3. 1 times 3 is 3. Then minus 9 times 3. So this gives us 7. 1 plus 3 minus 9 times 3. So this is 7 times 4 plus 9 times negative 3. Please, it is always good to check. We should have done that for the first one, but we checked it anyway. But it's always good to check this. After you get this, you do 7 times 4 is 28. 28 minus 27 is 1. Always good you do it. Okay? I think I said that in the videos on modular inverse. Okay, so inverse of 7 mod 9 is 4. Is 4. Okay? So we multiply 4 to both sides. Okay, we multiply 4 to both sides. So this will be 4 times 7 times P is congruent to 4 times 1. Everybody in mod 9. So this is a 28 times P is congruent to 4 in mod 9. So this means what this means is 28 mod 9 times P mod 9 is equal to 4 mod 9. That is what it means. 28 mod 9 is 1. So 1, because that is the essence of multiplying by the inverse. So we can have 1. That is the essence. Okay? So we can now have 1 here. 1 times P mod 9 this is congruent, okay? Congruent to 4. 4 mod 9 is 4. So P mod 9 is congruent to 4. So we know that P is equal to 4. We know that. Okay? We know that P is equal to 4. Okay. But let me say this. We are not going to, remember, we have not used the third congruence. We have not. We have not used the third congruence. So we have to be we have to be careful here by going, because that is the common mistake that students make. They just come now and substitute to get their x. No, you do that if it's for two linear congruences. When you come here, that is not two linear congruences, you have to go back to do this as an equation in P. You see how we did this as an equation in Q? I'm sorry, in X, in X. We have to do this as an equation in P. So what we have to do now is this. We have to say P is congruent to 4 in mod 9. That is what we have to do. So please do not go and substitute, because you have not used the third congruence. You have not done that. And that is the way, if you have 4 congruences, 5 congruences, no matter what, this is the way you have to do it. So don't come here immediately and go and substitute. No. Because we have not used the third congruence. So what we have to do is, we still have to establish the congruence here. Then we convert this to an equation. So we have equation 2. Okay? When we have 2 linear congruences, we had only one equation. Now we have 3 linear congruences, we shall have 2 equations. Okay? So we have this, P is congruent to 4 in mod 9. So this means that P minus 4 is 9. Okay, the first thing, P minus 4 is 9. And this means that P minus 4 is 9k, where k is a positive integer greater than 0. Just like here, P is a positive integer greater than 0. Here, k is a positive integer greater than 0. Okay, so P will be 9k plus 4. And we call this equation 2. Equation 2. Equation 2. Now you have to be careful on this. You have to be very careful on this. Okay? So we have found P to be 9k plus 4. What we are going to now do is, we substitute this equation 2 into equation 1. So we find our x. When we now find our x, we now substitute that in congruence 3. See that? Because we will now get something in k. Okay? So we'll substitute 9k plus 4 for P in equation 1. In equation 1. Substitute 9k plus 4 for P in equation 1. So equation 1, we have that x is 7p plus 2. So what we now do is, we now have that x is 7 times 9k plus 4 plus 2. Okay? So this will be, x will be 63k. 7 times 9k is 63k plus 28 plus 28 plus 2 plus 28 plus 2. Right? So our x, if I bring it here, is now 63k plus 30. And I will call this equation 3. I'll call this now equation 3. Okay? Equation 3. Now, we will now do this. So I'm going to erase from here. The next thing we'll do is we substitute equation 3 into congruence 3. Because we have to use everybody. We have to use everybody. Or we can say substitute 63k. You can say substitute 63k plus 30 for x in congruence 3. In congruence 3. Okay? So, congruence 3 is x is congruent to 5 in mod 10. So, we now have 63k plus 30 is congruent to 5 in mod 10. Subtract 30 from both sides. Subtract 30 from both sides. So 63k is congruent to 5 minus 30 in mod 10. So 63k is congruent to negative 25 in mod 10. Okay? Please don't find negative 25 mod 10 right now. Just let's do this step by step. Okay, now let's get inverse of 63 mod 10. That's what we need. Inverse of 63 mod 10. So we can multiply everybody by the inverse. Okay? So we find the GCD and then we get the inverse. Let's do that. So GCD of 63 and 10. So 63 is 10 times 6 plus 3, right? 10 times 6 plus 3. 10 is 3 times 3 plus 1. 3 times 3, 9. 9 plus 1, 10. 3 is 1 times 3 plus 0. So GCD is 1. But to get our inverse, we use this here. Okay, GCD, the divisor, is 1. But to get our inverse, we use from here. So 1 is equal to 10 minus 3 times 3, which is equal to 10 minus this 3 here is 63 minus 10 times 6. Now times 3, this 3 is this 3. This 3 is this 3. Okay? So this will be 10 times 1 minus 63 times 3 minus times minus plus 10 times 6 times 3. Okay? So this is 10 times 1 plus 10 times 6 times 3 is 18. 18. Then minus 63 times 3. So this is 10 times 1 plus 18, then plus 63 times negative 3. Okay? So this means that 1 is equal to 10 times 19 plus 63 times negative 3. Let us check it. 10 times 19 is 190. 63 times negative 3 is negative 189. So 190 minus 189 is 1. So this works. Okay, thank God, it works. Now, inverse of 63 mod 10 is negative 3. So inverse of 63 mod 10 excuse me excuse me is equal to negative 3 mod 10, and that is 7. Negative 3 mod 10 is 7. Okay? Now we have to multiply 7. This is 7. We now multiply everybody by 7 here. I mean, you know, every side, both sides. We multiply both sides, not everybody, but both sides by 7 here. So this is 63 times 7 times k is congruent to, or let me just say 7 times 63. That's fine. 7 times 63 equal to 7 times 63 times k is congruent to 7 times negative 25. Okay, everybody in mod 10. Okay, let's save time. So let me bring my calculator. I mean, I can do it offhand. But let's save time here with calculator. I mean, 7 times 3, 21. 1, 2, 7 times 6, 42. Plus 2, 44. Okay? So 441 times k. 441 times k is congruent to negative 7 times 5 is 35, 3. 7 times 2, 14 plus 3 is 17. Negative 175. Okay, everybody mod 10. So this means that 441 mod 10, okay, times k mod 10 times k mod 10 is congruent to negative 175 mod 10. Okay? 441 mod 10, of course 440. Okay, this is 1. That was the essence of doing that. So we now have 441 mod 10 is 1. K mod 10 is still K mod 10. No problem. Let's have it as K mod 10 to be K mod 10. And then negative 175 mod 10. Actually, you see, I'm not using calculator. I'm not using calculator. Okay, negative 175 mod 10. Remember our division rules. 175 divided by 10, that's 17. 17, which is negative 17, remainder negative 5. Right? This is this gives us negative 17, remainder negative 5. Negative 17 times 10 is negative 170. Minus 5, negative 175. However, we don't want remainder that is negative. We don't. Remember that. Okay, in the videos we did, we do not want a negative remainder. No, the quotient can be negative, but the remainder should not be negative. Okay, so so what do? We just increase that. Negative 17 minus 1, negative 18. So this will be now negative 18 remainder, negative 18 times 10 is negative 180. Now to get it to negative 175, you have to add 5. Remainder 5. Okay? So negative 175 more 10 is equal to 5. Alright, so let's finish this up, folks. Let's finish it up. So we now have that. From there, 1 times k mod 10 is equal to 5. So k mod 10 is 5. So k is 5. K is 5. K mod 10 is equivalent to 5. Equivalent to 5. So k is 5. 1 times k mod 10 equivalent to 5. So k mod 10 is equivalent to 5. 5 mod 10 is 5. So k is 5. So let's finish our work here. So our x will now be 63 times 5 plus 30. Our x will be 5 times 3, 15. Carry 1. 5 times 6, 30. Plus 1, 31. 315 plus 30. So our x is 345. Yay! That was what we got in the previous video. Yes. Okay, so let us check it. 345 divided by 7. We want to check it to make sure everything works. 345 divided by 7, 49 point something. 49 times 7, 343. Subtract from 345, 2 works. 345 divided by 9 is 38 point something, the integer part. So 38 times 9, 342. Subtract from 345, 3. 345 divided by 10 is 340. Remember 5. 34, remember 5. Okay, I mean it's 34, remember 5. Okay? Alright, so thank God it works. Okay, so I think I like this method. You just have to be extra careful if you have more than 2 linear congruences. Okay, remember, if you have 3 linear congruences, you have to use all of them. So after you get the value of the second one, P, you have to put it as write it as congruence, write it again as an equation. Go back and substitute it as x. Okay, that is why we call it back substitution. Substitute it back for x with the new variable. So you now use it in the third congruence. Okay? If you have any questions, please feel free to ask. Alright? And you can use, if your professor does not specifically say the method he or she wants you to use, then use any method you like. Okay? Thank you for listening, and you have a great day.